45th lecture, and we are going to discuss the rest of RC synthesis and introduce also RL one port synthesis, two element kind. Let us recall the properties of RC impedance and admittance, because they are not similar, they are not identical, the properties are different. Let us make a short review of the properties of RC impedances and admittances. You recall that starting from the most general Foster 1 form of RC impedance, that is impedances of this type, and the most general form for RC admittance, which is R in parallel with C and then a number of RC in parallel. Starting from this, we derived the general forms for RC impedance and RC admittance. The general form was K0 by S due to this capacitor plus K infinity due to this resistor plus summation of terms like Ki divided by S plus sigma I, where Ki's and sigma i's are expressible in terms of the individual resistors and capacitors, and therefore all these coefficients K infinity, Ki and sigma I, they are real and positive. On the other hand, when we took an RC admittance, we saw that it is of the form K0 because of this resistance plus K infinity S because of this capacitor plus summation of terms like Kis divided by S plus sigma I. This is the difference that occurs in S here, because R and C in series, if you take the admittance, their admittance is of this form. In other words, these Ki's are not the residues of YRC. And you also notice that ZRC and YRC only differ by a multiplication by S. That is, if you multiply ZRC by S, the form is the same as that of YRC. Another way of expressing this is that YRC by S is of the same form as ZRC. All right, and from these two expressions, and this similarity, we derived several properties of RC impedances and RC admittances, and these are as follows. I keep the expression here so as to facilitate appreciation of the properties that I am going to mention. K0 by S plus K infinity plus summation Ki by S plus sigma I, then K0 plus K infinity S. Just multiply this by S and you get the general form for YRC. It is Kis divided by S plus sigma I, and the first thing you notice is that poles of ZRC, that is this sigma I, since they are real and positive, and the other pole is possible at S equal to 0, the origin, so poles must be on negative real axis. And the same applies here, poles on negative real axis. And what are poles of YRC? Are the zeros of ZRC. Therefore, I can say poles and zeros of RC impedances must lie on the negative real axis. All right. Then we look at the situation at infinity. There is no way that ZRC can have a pole at infinity. There is no way. Yes. Fine. That is also negative real axis. Infinity is a single point. Whether you go from this side or that side or this side or that side, infinity is a single point. And when convenient, we consider it on the negative real axis. When convenient, in the LC case, for example, we consider it at plus j infinity. Okay. Since we don't know it, we can put it anywhere. It's exactly like a concept of God or heaven. Okay. Infinity is very similar to that concept in various religions and so on. What we said was, if what are poles of YRC are the zeros of ZRC. So we conclude that poles and zeros of RC emittances all lie on the negative real axis. Then the situation at infinity, there is no way that ZRC can have a pole at infinity, no pole at infinity. Pole at infinity is not permitted, all right. At infinity, what can happen is that the value can be either k infinity, either a constant or 0 at infinity. On the other hand, YRC can have a pole at infinity, pole, or if it has no poles, then it is a constant at infinity. Okay. And similarly, similarly at the origin, it can, ZRC can have a pole because of this term, or a constant at origin at s equal to 0. On the other hand, for YRC at s equal to 0, it is either a constant which is equal to k0, or 0 at s equal to 0. Well, if you look at the properties of ZRC, this property at YRC is obvious. Okay. If ZRC has a pole at infinity at s equal to 0, obviously YRC has to have a 0, right. So, it is a reciprocal property, but nevertheless we list them out separately. Yes. Okay, this point we did mention earlier. K0 is not a residue, because no pole, there cannot be a pole at the origin. Pole at the origin is not permitted. K infinity is a residue, because K infinity is the residue of the pole at infinity. However, these Ki's are not residues. They are residues of YRC by S, not of YRC. All right. Okay, we continue this discussion. ZRC YRC, K0 by S plus K infinity plus summation Ki. This is the kind of a Bible for RC impedance or admittance synthesis. If you remember this, everything else follows. That is why I am repeating this in every slide. K0 plus K infinity S plus KIS divided by S plus sigma I. Now, since the question of residues came, residues here K0, K infinity, Ki, they are all residues. Residues are real, is not a residue. Okay. So, K0 and Ki's, they are all real and positive. Whereas, if you find the residues of YRC, not YRC by S, you can show that they are real but negative. We shall demonstrate this with the help of examples, but we will not prove it. It will come out to be negative. There is no other way. We also showed by taking the value of ZRC on the real axis, that is sigma, and by differentiating this with respect to sigma, we showed that this has to be strictly negative. If you do the same thing with respect to this, that is, you put S equal to sigma and differentiate, you can show that YRC of sigma with respect to sigma would be strictly positive. It would be strictly positive. And as a corollary to this property, that is, the slope is strictly monotonic, it is either strictly negative or strictly positive. It follows that poles and zeros in either case have to alternate. There is no other way. Poles and zeros alternate. This is a consequence of this slope property. They have to alternate. In addition, for ZRC, the first critical frequency has to be, for ZRC has to be a pole. first critical frequency has to be a pole, and it follows that for YRC the first critical frequency must be a 0. Last critical frequency must be a 0, and last critical frequency here last critical frequency LCF, this must be a pole. All right. If you plot the sketches of YRC versus sigma, it is very easy to show that the first critical frequency must be a 0 for YRC and it must be a pole for YRC. And it also follows that the infinite frequency value of ZRC, ZRC infinity, is less than ZRC 0, and because admittance is reciprocal, YRC of 0 must be less than YRC of infinity. If the two values are constants, okay, if ZRC has a pole at the origin, then obviously it is infinity, the value is infinity. If YRC has a pole at infinity, obviously it is infinitely large. Now, not only that, yes, so the value is infinity, which you do not know what the value is. Nevertheless, if it is a constant, then this constant must be greater than this constant. That is what it means. If it is a pole, then we do not bother. Okay. Now, not only that, for ZRC we showed that ZRC of infinity is the minimum value of the real part of Z of j omega. We showed this, and in an exactly similar manner we can show that YRC of 0 is the minimum value of the real part of YRC of j omega, which means that in the synthesis problem you can always remove ZRC infinity without converting the rest of the function or the remainder function non-positive real. Similarly, here from YRC you can always remove the DC value. The rest of the remainder function shall still remain positive real. Okay. And then as far as synthesis is concerned, ZRC, YRC, the Foster 1 form can be synthesized from the partial fraction expansion of ZRC, whereas Foster 2 requires the partial fraction expansion of YRC by S. This has to be remembered. Cauer 1, did we discuss Cauer 1 in the last class? We concentrate our attention on the pole at infinity or the point at infinity. Okay. Let us look at Cauer 1 and Cauer 2, then we shall illustrate by means of an example. Cauer 1 synthesis, there is no harm in repetition even if I did this. Okay. ZRC cannot have a pole at infinity, right? RC impedance cannot have a pole at infinity. Recall the form. ZRC is of the form K0 by S plus K infinity plus summation KIS divided by S plus sigma I. This is the form. If you remember this, all properties, all synthesis should be obvious. Oh, how can I make that mistake? No S. All right. Now, Cauer 1 concentrates on the point at infinity. You see, at infinity what ZRC can have is either a constant or a pole. Now, this constant can be removed without affecting the rest of the function. So, I remove K infinity. If I remove this, then what will be the behavior of ZRC at infinity? It will be a 0, and therefore YRC shall have a pole at infinity, which I can remove as a capacitance. All right. If I remove that as a capacitance, then I take the reciprocal of that function. That will again be a constant, and which I can remove, and I can proceed this way till the function is exhausted. That is simple Cauer 1. Cauer 1 simply focuses on the point at infinity. Now, the starting point is important. Do you start from RC impedance or RC admittance? You see, if you remove the infinite frequency value of RC admittance, then you have made a great mistake, because you cannot remove that. From RC admittance, what you can remove is YRC of 0, not infinite frequency value. So, one must remember that if you want to develop in Cauer 1, you can remove two things are permitted, either the constant value from ZRC, the infinite frequency constant value from ZRC, or a pole from YRC. These are the two things that have to be done alternately, which means that what you actually do is to expand ZRC in continued fraction starting with the highest powers, all right, starting with the highest powers. The caution is that you can do this for LC functions either with impedance or admittance, it does not matter, but in the case of RC you must start from the impedance function, all right. This is Cauer 1. It would be more obvious when you take an example as far as, yes. Oh, the last part. Question is, suppose we had a, suppose we invert this YRC, okay, YRC is d by n. Can I do a continued fraction expansion starting with the highest powers with YRC? No. What would that mean? If I do this, what would that mean? It would mean removing the constant value at infinity from YRC, which you cannot do, right. What we can remove from YRC is its DC value, not the infinite frequency value. Okay. Cauer 2 focuses the attention on the point at the origin, s equal to 0. Okay. This is the point which you look at. Now, at s equal to 0, what is it that we can remove from an RC emittance function? Obviously, it is constant from ZRC or YRC? YRC. Therefore, Cauer 2 must start from YRC. There is no other way. What you do is you look at YRC, which is K0 plus K infinity S plus summation Ki S divided by S plus sigma I. You can remove from YRC the constant value K0, and then if you remove this, if you remove K0, then YRC has a 0 at the origin. So, ZRC shall have a pole at the origin, which you can remove as a series capacitor, and you proceed like this. So, what you get is shunt resistors and series capacitors. Okay. This is Cauer 2. Once again, Cauer 1 has to be started with impedance, Cauer 2 with admittance, and this can be formalized by making a continued fraction expansion starting with the lowest powers, okay, starting with the lowest power, that is, you divide P onto Q, but write them in reverse order, that is, the constant term comes first, here also the constant term comes first. What is the logic? Logic is that we are removing the DC value, that is the constant divided by constant value. Let us take an example to illustrate this, and this example we shall continue throughout today. Okay, our function is s plus 1, s plus 3. We will carry this out all through, s plus 2, s plus 6. The question is, realize this function as a driving point function. It does not say impedance or admittance. All right. The question is, realize this function as a driving point function of a 2-element kind network. Obviously, since the first critical frequency, first is realizability. Is it realizable by an RC network? Okay. First critical frequency is 0, 1, 2, actually -1, -2, -3, -6. So, they do alternate. The first critical frequency is 0, last is a pole, and therefore, if at all realized, it should be an YRC, not ZRC, because for ZRC the first critical frequency must be a pole, last critical frequency must be a 0. And therefore, for Foster 1 you have to take the impedance function Z of S, which is equal to S plus 2, S plus 6 s plus 1 s plus 3 and expand in partial fraction. One has to be careful. Does the function have a pole at the origin? No, it does not have a pole at the origin. So, we have to take the infinite frequency value k infinity. So, general form has to be k 0 by s if it is impedance plus k infinity plus summation k I by s plus sigma I. What is k infinity? No, oh it's 1, okay, s squared and s squared, that is 1, plus terms of this form we have two of them, s plus 1 s plus 3, this is k1 and this is k2, and I told you the trick to find k1 is multiply this by s plus 1 and put s equal to minus 1. So, we get s plus 2 s plus 6 divided by s plus 3 under the condition of s equal to minus 1, and you can do this very quickly, 1 5 2, therefore 5 by 2, 2.5. We will not use the decimal fraction, still we can, okay, because decimal might require a truncation which you do not want to do. We will continue fractions, rational numbers as long as possible. If it becomes very large, then you go ahead. What is the danger? Suppose you truncate, what is the harm? The harm is that in continued fraction things will not cancel. If you truncate somewhere in continued fraction, things will not cancel, okay? Because in Foster 1 is an end by itself, you do not have to do anything further. But in Cauer 1, once you Cauer 1 or Cauer 2, once you do truncate, you are in trouble. So, do not truncate. Similarly, you can find k2 is equal to, if I am not mistaken, 3 by 2. Okay. Therefore, my z of s is 1 plus 5 by 2 divided by s plus 1 plus 3 by 2 divided by s plus 3. Now, do not try to play smart here, because 5 by 2 may become 2 by 5 in the element value and things like that. So, have the patience to write this as 1 over 2s by 5 plus 2 by 5, then element values shall be obvious. Similarly, here you write 2s by 3 plus, yes, 2, okay. Then you draw the network, 1 ohm, and then you have as a parallel RC, another parallel RC corresponding to this term, and that goes back, this is my Foster 1, the capacitor here would be 2 by 5. Since this is impedance, the reciprocal would be an admittance, and the resistor here would be 5 by 2, not 2 by 5. This is CS plus G, SC plus G. Similarly, this will be 2/3 and this would be half. That is the correct value. Alright, this is Foster 1. Let us look at Foster 2. The function is YRC is equal to S plus 1, S plus 3, S plus 2, S plus 6, and in Foster 2 we have to divide by S, so we divide by S and expand this into partial fraction. The first quantity would be K0 by S. K0 here is 3 divided by 12. So, 1/4 S, 1/4 divided by S, which is 1 by 4S. Is that okay? K0 should be obvious. Put S equal to 0 except for this term, then 1 into 3, 3, 2 into 6, 12, 3 by 12 is 1/4. So, I have written 1 by 4S. I could have written 1/4 divided by S, this is K0, but I have saved one step. Plus you shall have some let us say M1, I used K earlier, but it does not matter, M1 by S plus 2 plus M2 by S plus 6, and you can find out, I will skip these steps. M1 in my case it came to 1/8 and M2 was 5/8. So I can write down YRC is equal to 1/4 plus, okay, now I multiply by S, 1 by 8 S divided by S plus 2 plus 5 by 8 divided by S plus 6. And as I said, do not try to play smart, write this in terms of a realizable quantity, that is, here it would be 8, agree?
5 by 8s.
Yes, 5 by 8 S multiplied by S, okay. Thank you. So I get 8S plus 16 divided, so 8 plus 16 divided by S plus, what do I get here? 8 by 5 plus 48 divided by 5S. Agree? And accordingly, now I can draw the Foster 2 network, as we always indicate resistance values. So this resistance would be 4 ohms, and then we shall have 2 RC series networks in parallel. The resistance value would be 8, agreed? Reciprocal of admittance is impedance. Here also the resistance value would be 8 by 5, and then R plus 1 over SC. So this capacitance would be 1 by 16, and this would be 5 by 48, and your Foster 2 is complete. Foster 2. Now suppose we forgot that we have to divide by S. Let us see what happens. It is worth doing at least once. S plus 1, S plus 3 divided by S plus 2, S plus 6. Suppose I expand this in partial fraction, then you see, if I write this as, what are the things that I should write? I should write the infinite frequency value. Okay, that means 3 divided by 12, which will be 1, I am sorry, this is 1, plus some K1 by S plus 2 plus K2 by S plus 6. Let us see what K1 comes out to be. It would be S plus 1, S plus 3 divided by S plus 6 under the condition S equal to minus 2, which becomes negative. Similarly, you can show that K2 is also negative. It can be strictly proved, we do not need to. Expansion of Y.
So what about K0?
What about K0? K0 is 1 by 4, but shall we take K0 out? Yes, we can. We should? Not necessarily. Actually, this expansion should not be done. So let us not discuss it further. Okay. It's like learning spelling. One doesn't learn spelling by giving you a wrong spelling, because that gets imprinted on your mind. So let us not consider this further. You must remember that YRC, a sacred tie, sacred knot is to be tied around it by division by S. Otherwise, the expansion is not valid. Let us look at Cauer 1 now. For Cauer 1, we have to take the impedance function. Because it is RC, we have to take the impedance function and write it as a rational function, not in terms of the factors, but in terms of a polynomial. And I get S squared plus 8S plus 12, S squared plus 4S plus 3. Is that okay? All right. Now I start continued fraction expansion. S squared plus 8S plus 12. The logic is that we are removing the infinite frequency constant value from Z of S. So I get 1 S squared plus 4S plus 3. Let me bring the remainder here. 4S plus 9, that divides S squared plus 4S plus 3. Do not forget to indicate the dimensions. This is a Z. Then I get S by 4, S squared plus 9 by 4S, and this is an Y. So I bring the remainder here. 16 minus 9 is 7 by 4S plus 3 divides 4S plus 9. The numbers start getting
16.
16 by 7. Oh, I might have made a mistake. This is an impedance. So 4s plus 48 by 7, 48 by 7. So 63 minus 15? 15 by 7. I did make a mistake. 15 by 7, that divides 7 by 4s plus 3. So I get how much? 49 by 60. Correct. S, isn't that needed? S is needed. This is a y. So I get 7 by 4s. Then remainder is 3 divides 15 by 7. So 5 by 7. This is a Z impedance. Okay. In other words, my network shall be, well, let me write this continued fraction. This is 1 plus 1 over s by 4 plus 1 over 16 by 7 plus 1 over 49 by 60 s plus 1 over 5 by 7. Is that correct? And the network should now be obvious. My network would be 1, then a capacitor of value 1/4, then a resistance of value 16 by 7, then a capacitor of value 49 by 60, then a capacitor, a resistor of value 5 by 7, and that's it. This is Z of S, and this is my Cauer 1. Had you started this with Y of S, you would get negative values, and that would show that you have to go back. But I hope you would not make a mistake. If it is a ZRC, you start continued fraction with the highest powers. Alright, if it is to be Cauer 1, no, it is the other way around. If it is to be Cauer 1, then you start continued fraction of ZRC starting with the highest powers. Let us look at Cauer 2. Cauer 2, you have to take Y of S. It is RC, you have to take Y of S, and you write the rational function in the reverse order. That is, you write 3 plus 4s plus s squared divided by 12 plus 8s plus s squared, and then you start continued fraction, because you can remove y of 0, y RC of 0. 3 plus 4s plus s squared. If you make a mistake, if you try the other way around, you will immediately be corrected, but you lose time in the process. Okay. The first quotient would be 1/4. Is that correct? 3 plus 2s. This would be 2s plus s squared, 12 plus 8s plus s squared. So you get 6 divided by s. This is y, this is z. It has to be, because this will be a series capacitor. 6 by. What is this? Oh, how could you ignore that? S squared by 4. So there would be another term here. No, the coefficient of s squared would be
3s square by 4.
3 by 4 s squared. Okay. So is this okay? 6 by s? That will be 12 plus how much would be this? 18 by 4, which is 9 by 2 s, no s squared. So I get 16 minus, so 7 by 2 s plus s squared divides 2s plus 3/4 s squared. What do I get here? 4 by 7, and this is an admittance. So I get 2s plus 4 by 7 s squared. The numbers are not too bad. The remainder would be how much? 5 by 28 s squared. This divides 7 by 2 s plus s squared, and the remainder is, the quotient is 90.
8 by 5 s.
Oh, that's good. 98 by 5s. Yes, okay. 7 by 2s, and this is an impedance. Remainder s squared. The last step is very nice. 5 by 28, and this is an admittance. 5 by 28 s squared. The remainder is 0. The network can then be immediately drawn. If I write the continued fraction expansion like this, capital Y equal to 1/4 plus 1 over 6 by s plus 1 over 4 by 7 plus 1 over 98 by 5s plus 1 over 5 by 28. At least in the first few problems that you work out, you should write this. This is instructive, so that it's foolproof. After a little bit of experience, you may not write the continued fraction. You may write the element values right from the continued fraction expansion. So what we get is our network becomes a resistance of value 4, then a series capacitor of value 1/6, right? Then a resistance of value 7 by 4, then a capacitor of value 5 by 98, and finally a resistance 28 by 5. It's done. We have done Cauer 1, Cauer 2. All the 4 canonic forms have now been done. Now, once we have we know how to design and synthesize an RC network, it turns out that its RL networks are very simple to synthesize. Once we know how to do it for RC, for RL network, let's look at the let's go back and ab initio. The most general form would be this: a number of RL networks in parallel. This will be the most general form for Foster 1 configuration. And you see that if you call this R0, if you call this L infinity, okay, and you call this Li and Ri, then the expression would be, expression for impedance would be R0 plus S times L infinity plus summation. The equivalent of this is Ri S Ri Li divided by S Li plus Ri, which I can write as R0 plus S L infinity plus summation. If I take Li common from here, then I get S Ri divided by S plus Ri divided by Li. Okay, so far so good. Now the general form therefore obviously is K0. You understand why we write this as R0? At DC all the inductors is short, so this is the value at DC, and we wrote L infinity because at infinity it is this inductance which dominates. This is an open, but it's shunted by Ri. So at infinity it would be S L infinity plus a resistance which is finite, and therefore the value would be infinity. Okay, so the form is K0 plus K infinity S plus summation KIS divided by S plus sigma I, where all K's are real and positive, and so are sigma I's. And if you pause for a minute, you notice that this is exactly the same form as YRC, and therefore whatever we have said about YRC is applicable to a RL impedance. For example, if you want to expand an RL impedance in Foster 1, you have to first divide by S. All right, all that we have said about YRC now applies to ZRL, and by the same token YRL therefore shall be of the same form as ZRC. Just take the reciprocal of both sides. Alright, therefore, whatever we have said about ZRC does apply to YRL also. For example, the example that we took, pardon me?
For first two expansion we have to divide by 1 by. He told first one.
Foster 2, no, for Foster 1 we have to divide by S, because Foster 1 is an expansion of the impedance, and since the impedance is of the form of YRC, that is KI's are not the residues, you have to first divide by S, then do it. Okay? You see, Foster 1 is a series connection, Foster 2 is a parallel connection. That is the difference between them. And Cauer 1 is the point at infinity, Cauer 2 is the point at the origin. Okay? So, for example, if you want to expand an RL impedance into Cauer 1, then how would you start the continued fraction expansion? If you want to expand a ZRL,
So by small power.
pardon me, can you start with ZRL? No. Cauer 1 I am talking of. You have to start from YRL. Why? YRL has a pole at infinity or ZRL has a pole at infinity? So can you start starting with the highest powers?
Lowest power.
Well, let's look at this. Let's look at the same example. Maybe things would be clear. Our example was S. Okay, first, does this qualify to be a ZRL? Can this be a ZRL? Yes, because the first critical frequency is a 0. All right. So, okay. Now I want to expand. I want to get a Cauer 1 for this. Can I start expansion with the highest powers? That is the question I am asking. S squared plus 4s plus 3, s squared plus 8s plus 12. Can I go ahead and start continued fraction expansion? No, because if I do that, I shall be removing the infinite frequency value of ZRL, which is not permitted. Therefore, I must take the reciprocal and then start continued fraction. This is the point that if you do it blindly, you will come back. Let's say, don't do it again. Because you will get negative value. You see, you will get 8s here, so minus 4s and so on. Then you know you have made a mistake. You have to come back. Is the point clear? Similarly, if you want Cauer 2, can you start with ZRL? Yes, you
Yes, a
can.
low value.
That's right. You can start with ZRL. So, in Cauer 1 and Cauer 2, you have to be very careful. Similarly, Foster 1 and Foster 2, you will also have to be careful. Which one is to be divided by S?
ZRL.
ZRL or YS. Okay. Without any further spending any further time on RC and RL, we'll take further problems in the problem session. Can we go to an introduction to RLC? That is, if all the three elements are there, then what do you do? In general, RLC one port synthesis. In general, it has been found, very unfortunately, that the partial fraction expansion and continued fraction expansion, which works so beautifully for RC, RL and LC networks, doesn't in general work for RLC. And if you are lucky, it may be a combination of partial fractions and continued fractions does the job. Or maybe continued fraction starting with the highest powers, then switching over to lowest powers, then switching over to highest powers again. But it requires a lot of ingenuity. You cannot say right by looking at the function that it will work. In RLC one port synthesis, in general, partial fractions and continued fractions, or any combination of them may or may not work. And therefore, this remained a problem. This remained a problem for a very long time. Till in 1939, a gentleman, I think I mentioned his name, Otto Bruni, a German settled in the United States. Otto Bruni, in his PhD thesis at the MIT, Massachusetts Institute of Technology, proved that the most general synthesis of RLC 1 ports, most general and canonic synthesis. You see, all the synthesis that we have been talking about so far, 2 element kind, is canonic. The number of elements is exactly equal to the number of specs, nothing more, nothing less. You cannot do it less, you can do it more, of course. Okay? Otto Bruni proved that given, let's say, a biquadratic, let's say a biquadratic like this, s square plus a1s plus a0. Let's take the simplest form, s square plus b1s plus b0, where a1, a0, b1, b0 are constants restricted only by the positive real condition. That is, they are all positive and real, and they satisfy the real part condition. What was the real part condition? That a1, b1 should be greater than or equal to square root a0 minus square root b0 whole square. This is all that it is satisfying, nothing else. Otherwise, it is completely general. Bruni proved that, you see, you require 5 elements. Bruni proved that if you require a canonic synthesis, you cannot do it without a transformer. You cannot do it without a transformer. That is, a transformerless canonic synthesis is not possible. Okay? Let me state this. This is beyond the scope of this course, but I think you should know this. You should know the beautiful, elegant history that is behind one port synthesis. Transformerless canonic synthesis of RLC 1 port is an impossibility. Now, in between the advent of telephone, where filters were required, and 1939, there have been a lot of attempts at doing this, and there have been PhD thesis written showing impossibility of synthesis at all. Okay, that such things are not possible. You cannot synthesize an RLC 1 port unless you are lucky, unless a very special case occurs. Therefore, since 1939, lot of attempts have gone to prove or disprove Bruni, or more to disprove Bruni, but none succeeded. And therefore, the next effort was, well, don't insist on canonic. It requires 5. Maybe we are willing to give. See, a transformer is not a very favored element. A transformer has a lot of problems. Shielding, core, it becomes heavy, it becomes bulky, it picks up things, magnetic induction and things like that. Transformer, where you cannot do without a transformer, you have to. Power lines, for example, transmission, distribution, then in matching for audio frequencies and so on. But in general, if you can avoid a transformer, nothing like it. And this is why in power amplifiers, this complementary transistor that was invented, and it was a boon, because you could produce a power amplifier without using any transformer, in other words, very small size, and without any of those shielding and other problems. So people, pardon me?
Since biquadratic is the general form of the canonic equation for the RLC synthesis.
Biquadratic is the simplest form. You see, bilinear we know. Bilinear S plus alpha by S plus beta, it would be either an RC or an RL. Okay. So biquadratic is the first complication that arises. And people concentrated on biquadratic, because if you know how to design a biquadratic, you can possibly find out how to design others. So since 1939, people have been saying, all right, let's give up this fuss or insistence on canonicity. I am willing to use 6. Can you give me a transformerless synthesis? Well, unfortunately, this question remained unanswered till 1948, when two mathematicians, their names are Fialco no, I beg your pardon, Bott and Duffin. Duffin's excuse me, A. Bott and R.J. Duffin, two mathematicians. I don't remember where they were working, but Duffin is more than 100. He is still alive, and he has a special office at the university, at Carnegie Mellon, at Pittsburgh. Yes, Carnegie Mellon University. He has an office, and professor for life there till he lives. The beauty of this, they were, both of them were mathematicians. They were told by some of their electrical engineering friends that such a problem exists, and they looked at it, and in 1948 they published a half a column paper. Half a column means if you take a quarter size paper, well, half of this size, that much print with one figure in it. They proved that if you give up the canonicity, then transformerless synthesis is possible. Unfortunately, the number of elements that had to be used was 7, not 6. 7. And till to date, there hasn't been any improvement on this. So, transformerless canonic synthesis still remains a mysterious problem. Whereas practical networks are possible. You can build networks, you can analyze, you can build networks without transformer. But given a function, it's very difficult to do it. And the Bott-Duffin procedure then, after 1948, once again was subject of intensive investigation, because the demand for filters started growing up with an expansion of communication. The demand for filters grew up, and there are many attempts, and under very special circumstances one could reduce the number to 6, but not in general. It still remains a mysterious problem. We will continue this discussion in the next class at 12.